Let's look at some special cases of tensor products which are very important in their own right. So here's one application. This is something called extension of scalars. So here's the general problem. So first there is, let me talk about the dual notion, something called restriction of scalars. Okay, so what's this, what does this mean? So suppose I have two rings. So let R, S be rings, and let phi be a map from R to S, be a ring homomorphism. Okay, now what does this do? Any S module automatically becomes an R module. Okay, any S module N acquires an R module structure, it becomes an R module. So all this is left modules, an R module structure. So here I am not talking about commutative rings necessarily. It acquires an R module structure via the following definition. I want to make R act on an element n of n. Well, what I do is I first act phi to R. So this is now an element of S, and I am of course given that n is an S module, right? So then I just act on n. So this is this action now on the right hand side is the given action, the scalar multiplication of S on n. So when I say action, I mean the scalar multiplication. Okay, so this is my new definition. Okay, how am I going to make an element of R act on n? I will first convert that element into an element of S via this homomorphism phi, and then make that phi of R act on n. Okay, so this becomes an R module. Well, let's check the axioms of an R module. So axioms, let's check R module axioms. So what all do we need to check? Well, n is still a abelian group, that's all right. We just need to check things like, if I take R1 plus R2 and act on n, will it give me the sum? Is there distributivity? So this by definition is phi of R1 plus R2 acting via the given action on n, but phi is a ring homomorphism. Okay, so this is phi R1 plus phi R2 acting on n, and now by the fact that the n is an S module, there I have distributivity. So this is phi R1n plus phi R2n. Okay, so this by definition is R1 acting on n plus R2 acting on n. Okay, so I proved the first property. Now, so two things. One is, on the other hand, it's a on the right hand side it's a module over S, so those axioms are satisfied, and phi is a homomorphism of rings, so in some sense everything will carry through similarly. So property 2, for example, is R1 R2 acting on n. What's that? It's phi of R1 R2, which is the product, because phi is a homomorphism. How does the product act? Okay. Since n is an S module, okay, and that's what we need, because this is now R1 acting on R2 acting on n. Okay, axiom 3 says if I take R1 acting on n1 plus n2, or R acting on n1 plus n2, so this is phi of R, sorry, it's phi of R, usual action on n1 plus n2, but then this satisfies this axiom, phi R n1 plus phi R n2, again because n is n, again because of this reason. So that's R n1. And finally, the identity, if we take the identity element, the multiplicative identity of R, how does it act on n? Well, I first apply phi to it, but homomorphisms necessarily map the multiplicative identity to the multiplicative identity, and identity on n is n. Okay, so we have checked all 4 axioms. So this is what's called the restriction of scalars. Now, so what are the typical examples? So for example, if I had a vector space over the complex numbers can always be thought of as a vector space over the real numbers, right? Why is that? Because the ring, well, in this case a field, the field of real numbers has an inclusion map. This is my homomorphism phi, just an inclusion homomorphism. So the real numbers has a homomorphism to the complex numbers. So any complex vector space automatically becomes a real vector space, can be viewed as a real vector space by restriction of scalars. That's exactly the same definition. Okay, here it's just the inclusion map, and the inclusion map is exactly what corresponds more generally to restriction of scalars via a arbitrary homomorphism. Okay, observe, of course, many things change if I have a vector space of some dimension. For example, the complex numbers itself, as a complex vector space it's of dimension 1, but as a real vector space it's of dimension 2. Right, so this is a new structure in some sense, if you wish. Okay, now extension of scalars is sort of the opposite problem. So let's pose the problem here. Extension of scalars. Okay, so same thing, I am given a ring R and I am given a ring S. The question now is, suppose I have an R module. So let M be an R module. Okay, the question is, can one construct an S module from it? Right, this is like asking, I have a real vector space, can I somehow construct a complex vector space out of it? Okay, so it's sort of a vaguely posed question at the moment. But broadly, the idea is this: can you somehow go in the opposite direction? Okay, so the same thing that we tried earlier is not going to work anymore, because I only know how to make elements of R act as scalar multiplication. If you're given an element of S, I don't have a way of converting it into an element of R, right? Because the map phi only goes in this forward direction. I can't apply phi inverse. There is no such thing as phi inverse. Phi need not be invertible, for example. Okay, so the point is, you can't quite do the same thing as before, but it turns out that one can nevertheless construct a useful notion of an S module which arises from the given R module M. Okay, and to do this we will use tensor products. Okay, so the answer is, well, there is a useful notion and we'll use tensor products. Okay, so let's go to the construction now and see how this is done. Okay, so again, for this we need this whole bimodules business that we talked about. So recall, I have my ring. So okay, there's R to S. This is a setup. The ring S itself, recall, can be thought of as a SS bimodule. Right? How was that? You have left multiplication by S and right multiplication by S. Okay, so via this is just multiplication in the ring. Okay, now the point is, because you have this, now there is, remember we know how to do restriction of scalars. So here is, imagine this is like your module N, right? N is a left S module. It's also a right S module. Okay. Now what I do is I do restriction of scalars to this. Okay. What I mean is I will now, by restriction of scalars, we may give S the structure of, well, what can I do? So let's just look at this, forget the second S on the right. So look at this S. S is a left S module. So by restriction of scalars, I can think of it as a left R module. Okay. So, and then I'll put back this S. Okay, so here's what I can do. I can make it into a left R module and keep the same S module structure as before. I can make it into a RS bimodule. Okay, what's the definition? Therefore, how should I make R act on the left? What does restriction of scalars say? You act phi, you will get an element of S and you make that element act as it is. And what's the right action? Well, that's as before, that I'm not changing. Okay, so this is now for all R in R, for all S in S. So this is how I make it into a right, rather into a bimodule, into an RS bimodule. Okay, now not just that, that's only one of the possibilities. We can also make it into a similarly S is an SR bimodule. You can do a similar thing, think of it as a SR bimodule. Okay, here I am restricting the action on the right via how does R act on the right, S act on the left as before. Okay, so on the what I have written here on the right sides are just the multiplications in S. Okay, good, and also as an RR module if you wish, also as an RR bimodule. Here I will change both of them. X acting on R is X multiplied by phi R. If R has to act on the left, then I will just restrict the action as before. So this is just restriction of scalars. Okay. Okay, good. So there are many different things you can do now, but let's focus for the moment on this one. Okay. Let's think of S as an SR bimodule. And what else was given? Let's go up here. We had M, which is an R module. So of course R module of course means it's a left R module. Okay, so now that means I can do something with tensor products. So M, recall, is an R module. Okay, so it's an RZ bimodule if you wish. Okay, or like when we said this before, it's only a left R module. Okay, you don't need to worry about putting the extra Z there. Now let's do the following. I'm going to tensor M with S on the left. Okay, in order to do that, I have to view S as a bimodule. Okay, so I recall I said it's an R, well, it's an SR bimodule. I want to think of S as an SR bimodule. Okay, and I'll think of M as an R module, or if you wish as an RZ bimodule. Okay, whichever way. Maybe we'll just put bimodules for now, RZ bimodule. Okay, so consider this. Consider this new object. Okay, now let's call this something. Let's call this f of m. Given an m, I have constructed a new object, S tensor m over R, where this tensor product, I make sense out of it like this. S is because it's a ring with a homomorphism from R to itself, I think of S as an SR bimodule via this equation star. Okay, this is my action. Okay, now given an SR bimodule and an RZ bimodule, I know how to make sense out of the tensor product. So this final object is therefore it's an SZ bimodule, becomes an SZ bimodule by our general discussion of tensor products and bimodules. Now this object is exactly what we mean by what we get by extension of scalars, because observe, to say that it is an SZ bimodule, I mean I can ignore the Z, right? The Z module structure doesn't add anything more, it's just the abelian group. So what I have therefore, i.e. this is an S module, is an S module. Okay, so this construction has done the following. M, on the one hand, I started out with an R module, a left R module, and starting with M, I constructed this new thing called f of m, which is S tensor M over R, and this new object is now an S module. Okay, and this guy is this construction is what we think of as extension of scalars. Starting with an R module, how do you construct somehow a natural S module from it? Okay, so this is, we say that this is obtained, Fm is obtained by extension of scalars. So this is the usual way it's expressed. F of M is obtained by extension of scalars from the module M. Okay, good. So what's the scalar multiplication also? Let's just recall, how did this become an S module, right? So S tensor M, firstly, what do the elements look like? Well, they look like summation Si tensor Mi. These are the typical elements now. Finite sums of this kind. Si's come from S, Mi's come from M, and again, as before, recall, this is not a unique expression. So there may be many ways of writing the same element as such a linear combination. Okay, but what is scalar multiplication? So recall, if I take a scalar S from S and I try to act on it. So if you recall how this whole bimodules business worked with tensor products, this is just obtained by multiplying the first component by S. This was the definition. Okay, so this is how scalar multiplication now works on this new module S tensor M. Okay, good. Now, what is the point of this? In what sense is this sort of the most natural module to which we want to associate to M? Okay, what's the special property that it has? That's the key. Okay, so here are the key properties. Well, let's call it a proposition. This new module S tensor M has the following two properties. Number one, there is sort of this natural map from M to this new module. Okay, let's call it, remember, there is a multiplicative identity in my ring S, so I can map each element M of M to S tensor M, I mean to one tensor M, that particular element of S tensor M. Okay, so observe this map. Now the point is that this map, what sort of map is this? This is an R linear map. Okay, so recall, on the left side, M is only an R module. Okay, so I can think of M as an R module. The right hand side, recall, was an S module, right? So when I say, so this guy is only, this was an R module, the right side is an S module. But what am I saying here? That this map, let's call it something psi, I claim that this is an R linear map. What do I mean by that? Both sides have to be R modules for something to be, for this to even make sense. What I mean by this is, I view the right hand side, view S tensor M as, well, it's an S module, therefore an R module by restriction of scalars, as an R module by restriction of scalars. So that's something you can always do, right? So then I think of both as R modules, and then I claim that this map psi is actually an R linear map. Okay, so let's prove this proposition first, part 1 of the proposition. So how do I show it's R linear? Well, I have to show, if I take a sum of two things, what does it go to? One tensor M1 plus M2, and of course this map, this tensor symbol, you can think of it as, it's Z linear definitely. So one tensor M1 okay, therefore it's psi M1 plus psi M2. That's the easy property. Let's check the second one, which is that what happens if I put R in front of the M. So what is psi of Rm? Well, it's one tensor Rm by definition. Now recall this tensor symbol here is also R balanced, right? Because when I'm doing this, I'm sort of taking the universal property with respect to balanced maps. So if you go back and look, what I can do is move the R to the other side. So this is 1 times R, which is R again. Sorry, I had to be a little careful. So this is 1 is, maybe we should just be very careful with what belongs where. This is the multiplicative identity of 1, right multiplied by the element R, okay, tensor M. So this is the new right multiplication which I have. Now what is the right multiplication? If you go back and recall how we made S into an SR by module, the right multiplication is the following. If you want to right multiply by R, you just multiply ordinarily X with phi R. Okay, so I have to do that here. So I should make this, so X here is 1S, so when I multiply it by phi R, it just becomes phi R. Okay, so it's phi R tensor M. Now phi R we call, well, I can think of phi R as, 1 into phi R is phi R into 1. I can just put this 1S on the other side. Okay, so it's this element of S tensor M. But recall, that's exactly how the S module structure is defined, right? How did we define the S module structure? Here. So we said if you want to multiply some element by S, you just have to multiply just the first components of all the tensors by S. So here, what this means is if I take phi R acting on 1S tensor M, that's exactly, I multiply only the first component by phi R, okay? But observe, this is exactly saying, so phi R is just the R action via restriction of scalars, right? So this is just the R action on the element 1S tensor M by restriction of scalars. Okay, let's go back and see what that was. How did we define the restriction of scalars? This is the map. Right, when you want to make R act on something, it's just first apply phi and then make that element of S act on it. Okay, so lots of different definitions are sort of intermeshing here. So I would recommend that you sort of try and do this very slowly for yourself, check every step and see what's being used in every step. Okay, so that's exactly R psi of M. Okay, where the R action is the action by restriction of scalars. Okay, good. So what this means is that this map from M to S tensor M, which takes each M to 1 tensor M, is actually an R linear map. Okay, so that's the first observation. The second observation is that it is universal with respect to such maps. Okay, in other words, suppose I give you any, let N be any S module, okay, and let F be a map from M to N, be R linear. Okay, again, what do I mean by R linear? So recall, M is an R module, N is an S module, right? So when I say R linear, what I mean is you view the right hand side, view N as an R module by restriction of scalars. Okay, so when you do this, both sides become R modules and you can talk about R linearity. So F is an R linear map. Okay, given any such map, then there exists a unique map F tilde from, well, where is this map from? It's from this is a unique F tilde from the extension of scalars of M, from S tensor M R to N, such that two properties. One, this map is S linear now. Okay, so now observe F tilde, the right hand side is N is an S module, the left hand side is S tensor M, and that's also an S module, right? So it makes sense to talk about S linearity here, and so what we are claiming is you can this map F tilde will actually be S linear, and it will make the diagram commute. And to what diagram commutes? M going to S tensor M. So recall we had this standard map that we called psi, okay, which took every element M to one tensor M. Okay, then we have the given map F to N, and we claim that there is a unique map F tilde like this. Okay, so such that this diagram commutes. Okay, in other words, this diagram commutes. Okay, and recall diagram commutes just means that F tilde composition psi is the map F. Okay, so the claim is that you can always find a unique F tilde which is now S linear and which makes this diagram commute. Okay, so one way of phrasing this is to say that this extension of scalars construction is a way of converting R linear maps to S linear maps. Okay, good. So let's just see why this is true. So how would you construct this map? So let's just use the universal property. So consider the following: from S cross M to N, I take an S, I take an M. So what will I do? So I'll just say S acting on Fm. Okay, so this is well defined because remember N is a S module. So this is certainly defined since N is an S module. Okay, so this is some map. I claim that this map is actually R balanced. This map is R balanced. Okay, why is that? Well, property 1 is if I take S1 plus S2 comma M, that goes to S1 plus S2 acting on Fm, but that will split into 2 because it's an F module, it's an S module. Okay, since N is an S module, the S module axiom. Okay, and similarly the other, so this is all right, and the same for S comma M1 plus M2. Okay, similarly, so I'll just leave that for you to check exercise. And let's check the third and important axiom, which is that if I take S and I act it on the right by R comma M, what does that map to? Okay, that maps to, well, by definition it's S acting on the right by R times Fm, left multiplication. But how does R act on the S? How does R act on the right of S? So recall that's just S phi R. This is again by definition, okay, acting on Fm. Okay, now let's so then now they're all elements of S, so I can think of this as S acting on phi R acting on Fm. Okay, let's do the other side, which is S comma Rm. Okay, what does this map to under this map? Okay, so by definition again this is S acting on F of Rm. Okay, now what is F of Rm? So what we said is that F is R linear, right? So we had that property that F is R linear, so we can pull the R out, that's what it means. So this is S acting on R acting on Fm. Okay, but how is the R now acting? So we've got to be very careful. This is F because F is R linear. Okay, but now Fm is an element of N, which is only an S module. So how does R act on it? Well, by restriction of scalars. So what does that mean? To make R act on something, I first convert it to an element of S and then I act on it. Okay, since R action on n is by restriction of scalars. It's by restriction of scalars. Okay, and so that's the same answer as what we got earlier. So the third property is also true. So this map is in fact R balanced, and so now by the universal property, so by the universal property of tensor product, what does it mean? It says that there exists a unique map as tensor M. I have a map to n. There exists a map as tensor M. Okay, so we didn't give this map a name. Maybe we should have done that. So let's call this map G. Okay, and so this is G and this map is G tilde. Okay, so there exists a unique what sort of map? Well, this is a Z linear map. Right, that was the original universal product, G tilde universal property, such that this is the map alpha, G tilde composition alpha is G. Okay, i.e. what does that mean? G tilde acting on an element of form S tensor M will just give you G of that, which is, so it's G of S comma M, which is S acting on Fm. Okay, in particular, it means that G tilde acting on one tensor M is just one acting on Fm, okay, which is Fm itself. Okay, good. So G tilde is really the map that we want. Okay, so because G tilde certainly has the correct property that G tilde, when it acts on one tensor M, it gives me Fm. Okay, which means I now form a different diagram if you wish. So I have M and I look at my map psi M going to one tensor M. So I have argued that there exists a map G tilde F. Okay, so observe G tilde certainly makes this diagram commute. So G tilde composition psi is in fact F, right, because it maps one tensor M to F of M. And G tilde is definitely, you know, it's certainly unique. This property uniquely defines G tilde. That's because of this universal property. Right, from here we know there can only be one map which does this for all S and M. Okay, good. So now, okay, so what do we have to show? We have to show that G tilde is in fact S linear. That's the last part. So need to show G tilde is S linear. Okay, so let's prove that. How does G tilde work? What was G tilde? It was a Z linear map, right? And in fact, we know what G tilde does to a general S tensor M. It maps it to S F of M. Okay. So now observe how does G tilde act on summation Si tensor Mi. By definition is summation Si F of Mi. This is how it is defined. So this is by definition of G tilde. Now let's check what happens if you sort of multiply this by an S. Okay, so if I multiply this, so this is my element xi. So if I multiply this by S, so what is G tilde on S xi? Can I pull the S out is the question. Okay, by definition this is summation SSI F of Mi. Okay, and now observe that SSI F of Mi just means that you know, I can just pull this, you know, how so. Okay, so I've used something here, so let's back up a little bit. So S xi is by definition G tilde evaluated on S times this summation. But there we are using the S module structure on this tensor product, which is that you just multiply on the first component. So this is just summation SSI F of Mi. Okay, and now this just means I can pull the S out. So it's just S times whatever is left, and whatever is left was just G tilde of xi. Okay, so G tilde is in fact S linear. Okay, good. So we managed to show that this G tilde satisfies the property that we want, which is that, let's go back up, there exists a, so your F tilde is really your G tilde. So let's take F tilde to be G tilde. That's the end of the proof. Okay, now observe that what we have shown is that there exists, at least there exists a map F tilde which does the job. Okay, but why should this be unique? Well, there's still a little bit more to prove that this is in fact unique. Let's go back here. There exists F tilde which makes this diagram commute. That's what we have shown, and we have shown F tilde is S linear. What still remains to be proven is that such a map is unique. Okay, but I'm just going to leave that as an exercise. It's the same sort of thing that we have done before when we proved the various universal properties. The image of psi, okay, all elements of this form, they generate this as an S module. So that's the last thing that's left. Okay, it's again analogous to this. So to prove uniqueness, tilde use the fact that the image of this map psi generates as an S module. Okay, so prove this exercise. Okay, now once that's in place, then it automatically implies that this is unique. Okay, good. Now this is the sense in which really this is an extension of scalars. It's sort of the most I mean it's exactly the object you will construct such that every R linear map from the original module M to some S module factors uniquely through this extension of scalars module. Okay, and all of this can sort of be let me just make a couple of concluding remarks here. So you've looked at adjoint functors and so on. So all of this can be phrased beautifully in terms of the nomenclature, I mean in terms of the framework of adjoint functors and so on. So there are two functors here, the restriction functor and the adjoint and the extension functor. So without going into too many details, so on the one hand I have the category of R modules, and like I said, there's the category of S modules, and actually there are two functors now. Okay, one is the extension of scalars functor that we just defined called F. The other is the restriction of scalars functor F, G. So what is F? F takes a module N and sends it to this. Okay, and then this is what it does to objects. You have to similarly define it on arrows. And the other side, the G is the restriction functor. Okay, Gn is you just view N as an R module via restriction of scalars. Via restriction. Okay, so there is the extension functor and the restriction functor, and it turns out that these two guys are actually an adjoint pair. Okay, the extension comma restriction is an adjoint pair of functors. So they're both functors, and further they form an adjoint pair. Okay, so this is something you might want to try and prove for yourself. That's really what the previous proposition says, that it exactly meets the definition of an adjoint pair. Okay, that's one. The other remark I wanted to make is that so this particular notion of extension of scalars is an extremely important notion. It's not just, this has lots and lots of applications. So it's not just trying to construct a real vector space, trying to make a complex trying to make a real vector space into a complex vector space in some sense, trying to define an action of the complex numbers. That's of course one that, for example, occurs in linear algebra in several places. But this sort of thing appears in finite group representation theory and so on, where often you have a subgroup H of a bigger group G, and you somehow want to study what are called modules or representations of H. So you have representations of the smaller guy, and from those you want to construct representations of the larger group. Okay, representations are like modules. Think of it as modules. So this is a very important sort of thing, because the smaller object is often easier to understand, and from that you want to construct appropriate modules for the larger object. Okay, so it's the analog of saying I understand the ring R well, and I know how to construct modules over the ring R. Can I somehow use those modules to construct at least some nice modules for the ring S? Okay, so this is a very important sort of notion, and of course what we have done is really used all the things we have done until now, things like bimodules and so on. So it's the definitions are they're all intermeshed and somewhat subtle, so you'll probably have to work through this many times to ensure that you understand how every single equality comes about in every one of those equations. Okay, so I would encourage you to actually try and fight with this and ensure that you understand all these steps in the arguments.